So we've been doing double integration, now triple integration. So let's jump right in with an example, and you'll see that if you can make the step from single integration to double integration, then triple, and I guess there's quadruple or whatever, the process is pretty straightforward. So here's an example. I'm going to integrate with respect to x, then y, then z. So we're integrating over x, y, z. So our inner integral here is just me integrating with respect to x. So that works just like we would think it works. The y and the z are constants. So that's a straight add one to the exponent, divide by what's up top. So it's an x squared over 2. And it's going to be sub in the 0 to sub in the y. So those are these endpoints. Now we've done our integration. Let's stop for a second and look at this step. We are integrating with respect to x. These endpoints have to do with the dx, so they're x equals 0 and x equals y. So it's going from the curve, or the surface, in this case the surface, x equals 0, that's a plane, to x equal y, that's a tilted plane. But mechanically, it's just going to be straight sub in the top minus sub in the bottom. So I'm going to get y squared over 2 minus 0 for this. So y squared over 2 minus 0, done. And now we'll just do this other integration with respect to y. And then that's going to go from y equals 0, a surface, a plane, to y equals z, another tilted plane. So when I integrate this with respect to y, that's going to be y cubed over 6. So add one to the exponent, divide by what's up top. And now I'm subbing in the z, sub in z, that'll be z cubed minus 0, the minus 0 I'm not writing. And now we just got to integrate this last piece here. That's going to be another add one to the exponent, divide by what's up top. So that's going to be z to the 4th divided by 24, sub in the top minus sub in the bottom. So let's put that in there. We're starting at this time it's the line z equals, or the value, let's say the value, the number z equals 1 to the number z equals 2. Just like when we did double integrations, the last integral, the last endpoints are numbers, same thing here. So when I sub in 2, I'm getting 16 over 24 minus 1 over 24, and final answer 15 over 24. So the point of this example is that the mechanics of triple integration is exactly the same as you think it is how we did double integration. But here we weren't imagining any shape, we were just mechanically going through the integrate, sub in the top, sub in the bottom. Let's look at something where we have to think about, an example where we're going to have to think about things. But in general, in triple integration, we're integrating a function, this time it's a function of x and y and z, over a volume. So that dv can be written as, well, dx, dy, dz, or, any combination of that. So dy, dz, dx. I guess there's going to be 6 different versions of this. I don't need to write them all down, but you just pick like one order of dx, dy, dz. And as you'll see in some other, you can see in some other places that you can switch coordinate systems. So dv can also be like with thetas and phis if you go to spherical coordinates. We're not doing that in this video. All right, let's do an application. We want to set up the integral. So here they don't even want us to actually evaluate it. We're trying to get the volume of this paraboloid. Now this curve is This is the curve z equals 1 minus x squared minus y squared, plain vanilla paraboloid. And so we want it below that curve and above the z equals 0 curve. So let's shrink that to see. We only want to see the from 3 up. Sorry, from 0. So we're just looking for the volume of this shape. Now, if we really just wanted to find the volume of this shape, a totally easier way to do it would be, I'm trying to spin it around, like, anyway, a volume of rotation is what I'm trying to say here. So you'd be spinning this parabola around the axis. A volume of rotation, shell method or disk method, would be way easier than what I'm going to do now. But I want to show an application of triple integral. So we're looking at this footprint here. Now, we want this to be a triple integral. Why? Well, because we're in the triple integral section. I guess that's why. But this seems like the easiest way to do it would be volumes of rotation. The second easiest way to do it would be, well, why isn't this just a double integral over the footprint, that x squared plus y squared equals 1 circle? Why isn't that just a double integral? Sure, but the question is set up the triple integral. So they want me to do this as a triple integral. So I'm going to be integrating this, but I want to find a volume. So just like when we integrated double integrals to find an area, our function was 1. I'm going to do the same idea. So I'm integrating over a volume. So I'm going to pick this to be dz, dx, dy. Z, dx, dy. And now z is going to go from z equals 0. That's the curve, that's the bottom. To z equals this 1 minus x squared minus y squared. Now when I integrate 1, I'm going to get z sub in the top minus sub in the bottom. It's going to, like, in one step turn into the double integral that we would have done earlier to calculate the volume. But we wanted a triple integral, so we have that. And now x is going to go, so I'm going to go back to this, shape. X is going to go from, set this up with x and y. X goes from this side of the circle to this side of the circle. So this is the side of the circle that's x equals, whole circle is 1 minus x squared minus y squared. Let's clip this then. Let's see. The whole circle, this circle, is x squared plus y squared equals 1. But I want to solve this for x. So that's going to be x is equal to plus or minus 1 minus y squared. That's this side. This side is x equals plus 1 minus y squared. Now there's symmetry, so I could go from 0 to the top or to the side and double it and all that. But this is to set up an integral, so I'm not worried about simplification. So now my my middle integral is going to go from x equals minus 1 minus y squared to x equals root 1 minus y squared. So let's get back to that. So my inner integral here minus root 1 minus y squared to the top. All right, now finally there's y's. Those are going to be numbers. Lowest y in the shape, highest y in the shape. And we're done. They just wanted us to set it up, and we did. If I were to do this integral, we would get the same answer as we would have done with volume of rotation. But this one is a setup and do not evaluate. Well, it doesn't say do not evaluate, but it just says setup. Let's find a volume then by, find a volume of a solid bounded by these curves. So it's a volume. The function we're going to integrate then is 1. We're just summing up all of the volumes. Let's take a look at the shape here. We're talking about being below this curved surface on there's the origin. So underneath this curved surface on this side of that plane, that's the plane x plus y equals 4, and above z equals 0. So this, underneath this curved surface to this side of that plane and in that box. So in order to set this up as simply as possible, let's start with z again. Throughout this whole shape, it starts on the curve z equals 0 and goes to the curve z equals e to the x times y through this whole shape. So we're going to start at the curve z equals 0 and go to the curve z equals e to the xy. Now that means I'm starting with dz first, like we did before, and that will turn it into the double integral that we would do if we were trying to do that volume with the double integral. All right. Now, should I do x first or y first? Well, let's take a look here. I'm looking at how x goes through the whole shape. X always starts on this x equals 0, and throughout the whole shape ends on that plane throughout the whole shape. We've already got this into consideration. I'm just looking at essentially the footprint. So I'm going to go from x equals 0 to the x equals from the line. So I've decided to do x first, so x equals 0 to x to line. The line is going to be x equals 4 minus y. So I'm doing x next. So then y is the last one. Y is going to be lowest y in the whole shape as a number, highest y in the whole shape as a number. And this integral will produce the volume of that solid. Now, let's see an example of where we're not just integrating one. So I'm not doing this integral because I know you guys can just do it. It'll be z, and then they'll have to do some integration by parts. Anyway, a setup and do not evaluate, let's say. Next one. We want to do the density of a solid. Oh, okay. We're not just adding up all the little volumes to get a total volume. We're trying to get the density. Now, let's think about density. Density would be measured in something like kilograms per cubic meter. So if you had the density of gold, and I don't know what the density of gold is, but let's say it's like 1,000,000, and you had it 2 cubic meters of gold, you'd multiply 1,000,000 times you'd multiply the density times the volume. But if you don't have that's if you have a constant density. If you don't have a constant density, and this solid, this cube, does not have a constant density, it changes. I mean, the density is 0 right near the origin, and it goes all the way up to 1 right on this other corner. So we want to add up, we want to integrate that density. So I'm integrating that density function over the volume. And since it's a cube, I can do dx, dy, dz, because each one of them goes from x equals 0 to x equals 1. Y equals 0 to y equals 1. And finally, these outside ones are numbers, but they're z's. And if I evaluate this integral, I'm going to get the mass of the cube. I'm summing up all the little volumes times the density. All right, well, that begs the question then. Again, we haven't actually done that integration, but can we find the mass of any solid? Yeah, because if our density is not constant, then it's a function of our position, and then the mass is just going to be equal to the triple integral of the density over that volume. So the short answer, can we find the mass of any solid? Yes, a triple integral of that density function. So let's go back and actually calculate this then. We say it's not going to be too bad. Let's just do it. We're integrating this function with respect to x, the density function. So we're summing up over all the x's. So that'll be a straight, y is a constant, so that'll be an x squared over 2. And we're going from x equals 0 to x equals 1 because we're talking about this unit cubed here. So now that's going to be sub in the top for x minus sub in the bottom. So when we sub in x equals 1 minus when we sub in 0, you'll get a minus 0 there. So now let's do our integration with respect to y. With respect to y, that's going to be an add 1 to the exponent, divide by what's up top. Let's get rid of that minus 0. We integrated with respect to y. So we have to go from y equals 0 to y equals 1. And now this is going to be a sub in the top minus sub in the bottom for y. So now we're just going to be integrating a quarter. When I sub in y equals 1 minus when I sub in the 0. And that's going to be z over 4. It's a constant. And so when I sub in, well, let's do that. Let's do it. That's going to be z over 4 from 1 to 0. Finally, I get an answer of a quarter. So this all in all wasn't that bad. Could I have made it any better? Because density wasn't a function of z at all, what if I would have integrated with respect to z first? Because it was a cube, so we could do this in any order. Then I would have used this easier thing right away. Yeah, I don't think that would have been any easier. It was pretty straightforward. And units. If this is a density, then we're summing up a density. This will be mass. It'll be in like kilograms if the density was in kilograms per cubic meter.